Hey guys, how's it going? We are going to start reviewing today about polar coordinates. Um, they're very similar to how we actually come up with vectors and how we have the components of the vectors because we have an x and a y, and you'll see some very familiar formulas when we talk about changing from polar to rectangular and things like that. So, this is a way of graphing certain shapes. We can actually graph every single rectangular version of an equation using a different coordinate plane or different coordinate system called the polar coordinate system. And the way a polar coordinate is graphed is by going r, which is a specific distance from the center point. So if r is 5, we're just going to go 5 units outside or away from the origin, okay, the center of a circle. And then the other thing we need to know is what angle we should put that at. So we can define every single ordered pair, every single x and y coordinate, a left and a vertical movement, by saying how far away from the origin we go and then what angle should we graph it at. Okay? So, you can read some of the stuff on your notes there. I kind of explained most of that. So let's start going through example 1, which is just graphing an ordered pair. Okay? But these ordered pairs are given to us in polar form. Okay? So when we have polar form, and I want you to understand, I freehanded that, okay? It's pretty impressive. I got a little weird right here, but I did the best I could by freehanding. I don't have a compass like Mr. Moreland, so please forgive me for that, okay? Anyway, example 1, letter A, is asking for us to graph the point 2 pi over 3. Okay, so polar coordinates are always given to us as r theta. Usually, when we talk about rectangular coordinates, we go horizontally a certain distance and then vertically a certain distance. The way I normally graph polar coordinates is I think about my angle first and then go r units that direction. So I want to figure out which way should I be facing and then how far should I go. Okay, that's how I think about it. Either way is fine. Okay, you can think about I'm going to go out r and then go wherever your theta is. They both will land you at the correct spot. So I need to go to pi over 3. And I'm going to go out 2 units. So here's pi over 3. I'm going to go 1, 2 units. Okay, so I just graphed the point pi over 3, 2. Now I probably should label. I did not label what my r values are going to be. I tried putting some polar graphs, a link to a kind of a graph paper that has all of that on there that you can print off instead of trying to freehand all of that. So if your r is like 12, you're going to have to count by 2s or something like that. So make sure that that's 1, 2, 3, 4, 5, 6. Make sure you label the r coordinates, okay, how far out you're going. Okay, now, not only should we be able to graph that point, we should be able to rename that point a total of 4 ways, including this, so 3 more ways. And those 3 ways are going to be, or need to be, without going beyond 2 pi, okay? Or going beyond negative 2 pi. So I can actually name that spot a total of 4 ways, including this, so 3 more ways. I went to that spot by going pi over 3 units this way and 2 units toward that spot. I could rotate the other direction, okay? So that'd be taking my theta and subtracting 2 pi, and that would be going negative 5 pi over 3, okay? So I could go to negative 5 pi over 3. So 2 of my versions will have the same r value, but the way you get to that angle would be the positive direction and the negative direction. So I got that. The other thing we can do is we can make r negative, which means wherever you're facing, if r is negative, you're going to go the other direction, okay? So if I actually look at this angle right here, 4 pi over 3, but go away from it, I'll end up at that spot. So my next one would be negative 2, 4 pi over 3. Okay, so go to 4 pi over 3, but go away from it, -2. Got it. Okay, same thing then that we did before, how we had a specific angle. Well, that's rotating counterclockwise. We could rotate clockwise to this spot, so that's going 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, or 2 pi over 3, okay? But it's going to be -2 pi over 3 and -2, right? -2 pi over 3 takes me to this spot. -2 means that we're not going to go toward that spot. We're going to go backwards, lands me at that location. Okay, so I named it 4 different ways. I never crossed or went above 2 pi, even though I can rename that point an infinite number of ways, because I could go pi over 3, or I could add 6 pi over 3 to that, 7 pi over 3, 13 pi over 3. I can keep going rotations, but I don't want that. I want the 4 different ways of writing it, but without going above 2 pi, okay? So you guys can try the next one, pause the video, see if you can, first of all, graph it, and then rename it 3 other ways. And I'm going to start it, but you guys can pause. All right, letter B. 5, -pi over 6. Okay, so -pi over 6 means I'm going this way. I'm going out 5 units toward that. So 1, 2, 3, 4, right there is my ordered pair. But I can get to that spot 3 other ways. I could go a positive 11 pi over 6. And that's still going toward it. So it's still a +5. I usually give, the same R value, but just change my theta for the first one I write. Now I know the next 2 are going to be -5s. So that means I want to be going opposite. So I'm actually looking at this angle right here. This is 5 pi over 6. Or I can get the 5 pi over 6 by going -7 pi over 6. So those are my 4 different ways. Okay. Down below there is kind of the formulas for finding all of these different spots. We have our r theta, which was given to us. If you go to the right there, we can take that theta and we could subtract 2 pi. That's going to mean we're going to go the other direction. Okay. Or we could make it a -r and add pi, because we're going to go to that other angle, like that angle is linear. So instead of doing this way, we're going to go 180 pi and then go opposite to get there. Okay, and the next one you could go there and subtract pi to get to that spot. But I don't like learning formulas. I like understanding what that means. And if you understand it, you don't need formulas. Okay? Next question, or next part, is changing our polar coordinates to rectangular or vice versa. Okay, so think about this. If this point is r units away from the center, in our case it was 5 for our last problem, then I do have a horizontal and a vertical way of getting to that spot. So think about what we just created. We created a right triangle. So I know how to relate my r and my theta to an x and a y, because it's just a right triangle. So I know that, and I'll go through the formulas, but if I think about the cosine of theta, that'd be the adjacent over the hypotenuse, so x over 5. So I know that x is 5 cosine of the angle. Okay, and that's using this example here. Okay, or actually any of the examples I could do, because they're all the same point. Okay, so in other words, x is going to be whatever the radius is, however far out you go, because that's a hypotenuse, times the cosine of theta. Okay, we talked about that when we talked about vectors, right? And then same thing, if I do the same thing for sine of theta would equal, I'm running out of space. That was poor planning on my part. Sine of theta equals the opposite y over 5, or y would equal 5 sine of the angle. In other words, we have the formula y equals r sine theta. Okay, so how can you convert your polar coordinates to rectangular coordinates to an x and a y? R cosine theta, R sine theta. If we want to convert rectangular to polar, if I have an x and a y, and I'm trying to find r, that's a Pythagorean theorem. So I know that the r, the hypotenuse, is the square root of x squared plus y squared. Okay, and how do I find theta? Well, and if I know x and y, right, if I have rectangular, how do I find theta? Well, that's tangent. That involves tangent. I know the tangent of theta, this isn't my formula yet, but the tangent of theta is the opposite over the hypotenuse, so theta is the inverse tangent of y over x. So these formulas right here are the formulas we're going to be using for polar equations, okay? And even when we get to the calculus, we need to understand these formulas, okay? Calculus won't be until day 2, which is in 2 days, I think, okay? According to my plans. So the next thing is asking for us to convert our polar functions. Oh, it's those two. It's asking for us to convert that to rectangular, okay? So I know that this one, if I want it in rectangular, I'm going to have my x is 2 cosine of pi over 3. Cosine of pi over 3, we can do this, right? Unit circle. Cosine of pi over 3 is 1/2 times 2 is 1. Okay, so think about that. That looks probably over 1 unit. That makes kind of sense. The y value is going to be 2 sine of pi over 3. Well, the sine of pi over 3 is root 3 over 2. Times 2, we get root 3, which is what, 1.7 or something like that? Square root of 3. I'm in the wrong spot on my calculator. I was doing something. All right, here we go. Square root of 3. Yeah, it's about 1.7. So, yeah, because there's 2, right? If I go straight up 2, and that's coming down a little bit, remember, this was a rough sketch. So that makes sense. The next one, and it doesn't matter which version you use, right? They're all the same point. So we could use this version if I wanted to. If I want to find the rectangular form of that, then I would have x equals -5 cosine of 5 pi over 6, or any of those versions, okay? The cosine of 5 pi over 6, that's this spot, that is negative root 3 over 2, times -5 is positive 5 root 3 over 2. Okay, let's see what that is. 5 root 3 divided by 2, that is 4.3. Does it look like that? 1, 2, 3, 4, and a little bit. Yeah, okay, it's agreeing. And then to find the y value, that's going to be r sine of 5 pi over 6. So the sine of 5 pi over 6 is 1/2 times -5 is -5 halves. Okay, so down 2.5. Down, so there's down 2. If I kind of sketched my coordinate plane on here, right? Sketch my coordinate plane. So it's down 1, 2, and I would agree with that. Okay? So we can convert polar to rectangular. Example 3. Now, we do have to pay attention with example 3 here. This is converting rectangular to polar. I need to think about where that point is, okay? And I'll prove it to you as we go through this. All right. So, the point 2, 3. Right 2 and up 3. Even if I don't have my formulas memorized, right? If I just think about right 2 and up 3, I need to find this length and that angle. That's it. It's a right triangle, guys. Okay? So, my r, this is example 3a, my r is going to be the square root of 2 squared plus 3 squared. We get the square root of 13. And my theta is going to be the inverse tangent of y over x. And we can use our calculator. Pay attention to what your mode is so you know what the calculator is telling you, whether it's radians or degrees. I had mine in degrees, and I got 56.310 degrees. If you're in radians, it is 0.983 radians. Okay? So as an ordered pair, we have r theta. Okay, well that makes sense. You have 56 degrees. Root 13, square root of 13 is 3 point something. Okay? So that all makes sense. 3b. By the way, I knew that was going to be in quadrant 1. That's what I'm telling you. You got to pay attention, guys. That's quadrant 1. Let's look at this next one. We have the point 0, -5. We're converting this to rectangular. This is actually the easiest one because, or these versions, when it's 0 something or something 0, because if it's 0, -5, I know the distance it is from the center, so I know r. R is going to be 5. I could do -5. That's up to you. Okay, r is going to be 5, and I know that I would go 5 units, and the angle is 3 pi over 2. I don't need formulas to figure that out, because if I just go straight down, which direction is that? 3 pi over 2, or -pi over 2. And then how far are you going to go away from the center? You're going to go 5 units from the center. So I have the point 5, 3 pi over 2. And, you know, the other versions that you could write with that. All right, 3c. We have the point -4, -3. So if we use our formulas, our r is going to be the square root of 16 plus 9, so we get 5. Okay, that's our r value. And our theta is going to be the inverse tangent of -3 divided by -4. Now, if you plug that into the calculator, this is what the calculator gives you. In degrees, 36.870 degrees. In radians, it'd be 0.644 radians. Now, we have a problem. Because if I go 36 degrees, I'm pointing this way. If I go out 5 units, that's not where -4, -3 is. That's +4, +3. I'm in the wrong quadrant, but that's what my formulas tell me. Well, that's because the tangent of this angle is the exact same as the tangent of that reference angle over here in the third quadrant, which is where I'm supposed to be looking. Okay? So I know that I need to add 180 to that angle to actually get to where I want to go. This is quadrant 3. So pay attention to which quadrant you're supposed to be in, because trig, there are multiple locations that have the same values. You have to make sure you're at the right spot. Okay? That's not the right spot. I need to add 180 degrees or add pi radians. So my theta is actually 216, right? Did I add that right? Yeah, 216.870 degrees. Or if I write that in radians, I'm going to add 3.14 to that. I don't have that written down, but understand that I'm adding pi, which is the equivalent of 180 degrees. So I'm just going to put 3.78. I think 1's the next one. 5. I think that's what you would get. That should probably round up. I think that rounds up to 6. You can double check me if you care. Okay, but I'm in the ballpark. So my answer for this in polar form is 5, 216.870 degrees, not 36.870 degrees. Okay? I can make that negative, so that's another way I could fix it. I could go to this spot, which is up here, but go a negative r value. That's another way I could have named that and fixed my problem. Okay? So that's up to you. The next thing that we're dealing with is graphing polar equations. Now we're going to start off with some special cases, and then we'll look at the normal polar equations that we think of, like the rho and the cardioid and the lemniscate and all those things that are probably way back here in the back of the head here. But there are some basic shapes that the polar form of the graphs are kind of different than the norm, okay? But hopefully they'll make sense. The first one, letter A, r equals 2. That's just a circle. It's telling me the radius is 2. We don't have a specific angle that we're talking about. So if we graph that, and you have coordinate planes on your notes, if you have printed those off or if you picked them up in class, so we're just going out 2 units at every single angle, and we get our circle. That's a pretty good circle. All right. By the way, if I converted this to rectangular, remember our formulas? If I wanted to convert this to rectangular, I know something I can replace r with that uses x and y's, because r is equivalent to the square root of x squared plus y squared. If I square both sides, I get that rectangular version of that circle, which I already knew what it was going to be, okay? But those formulas, those 4 formulas, are how you can convert polar to rectangular, whether it's a point or it's an equation, and rectangular to polar, okay? Letter B, theta equals pi over 3. So now it tells me that the theta is a specific number every single r value. We don't have a specific r value. So this, if we graphed it, is pi over 3. It's that spot on my polar coordinates, right? Pi over 3. And it's all the r values, even the negative r values. Okay, so what do we get? We actually get a line. Okay? Now we could write the equation of that line, because I know that to convert this to rectangular, theta, how does that relate to y and x? Well, theta is the inverse tangent of y over x. So I can replace theta with what is equivalent to it. And I can take the tangent of both sides. Y over x equals the tangent of pi over 3 is root 3. And then we multiply the x over, y equals the square root of 3 times x. 1.7 times x. That slope is up 1.7 over 1. Okay, it goes through the origin. So we have a line in rectangular version. In polar version. Do you see how the polar form of some of these shapes that we've been dealing with is actually quite simple? The polar form of a circle, using calculus on this equation is going to be much easier than the calculus on this version. Using calculus on this version is much easier than the calculus on this version. So we've been dealing with the rectangular, but we're going to now deal with the polar of all this stuff. All right, the last one is r equals secant of theta. Ooh, I almost erased that. I want to keep that. All right, so letter C, we have r equals secant of theta. Okay, so I'm not really comfortable with secant in a lot of things. So I usually change them to cosine. A way to do that, since that's 1 over cosine, is multiply the cosine over. R cosine theta equals 1. Hey, you should look out for those formulas. They should jump off the page at you. R cosine theta is x. So this is just x equals 1. When I graph that on the polar equation, I go out 1 unit, and I know it's going to be a vertical line. Okay, out 1 unit, vertical line is where x equals 1. I got that. All right. Next page. We're going to do a few things with this. First of all, if you have a polar equation and it's not one of these shapes that we already know, making a table is usually the best way of graphing. Okay? Get the points and then connect the dots in the order that you're getting the points. That's important. So if I'm graphing example 5, r equals 2 cosine of 3 theta. I can make a table, plug thetas in, find r's, right? Because theta is the independent variable. R depends on what we plug in for theta. And then we're just going to start going through our thetas. A lot of times I'll count by pi over 6s. Usually that's enough. Sometimes you can count by pi over 4s. Maybe in the future we'll see when we can count by certain amounts. But pi over 6 should be enough. So 0, 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3, 5 pi over 6, 6 pi over 6, which is pi. I like to go 0 through pi on one of my tables, and then the other half of the circle I'm going to go in my other table. So that was 6 pi over 6. 7 pi over 6. 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. 11 pi over 6. 12 pi over 6 is 2 pi. Okay. So if you plug 0 in, cosine of 0 is 1 times 2 is 2. Plug pi over 6 in. Cosine of 3 pi over 6, right, got to multiply by 3. So cosine of pi over 2 is 0 times 2 is 0. So far I have 0, 2, and then it came back to this direction, it's back to 0. Okay, now I'm at facing pi over 3. So we got to multiply by 3. We get cosine of pi, which is negative 1, times 2 is negative 2. So facing pi over 3, we need to go negative 2. So we're down here. And then pi over 2, we get the cosine of 3 pi over 2, which is 0, times 2 is 0. So back to 0 there. 2 pi over 3, when I plug that in, I get the cosine of 2 pi, which is 1, times 2 is 2. So facing 2 pi over 3, we're going to go 2 units that way. 5 pi over 6, so that's the cosine of 5 pi over 2. 5 pi over 2 is going the whole way around and a half. So cosine of that spot is 0, times 2 is 0. Plug pi in, cosine of 3 pi is negative 1, times 2 is negative 2. So facing pi, we're going to go negative 2. I got an overlap. So everything else is actually going to overlap, and you'll see that. And maybe you probably see a pattern too. So 7 pi over 6 is going to be 0, right? 2, 0, negative 2, 0, 2, 0, negative 2, 0, 2, 0, negative 2, 0, 2 pi is out to 2. But hopefully you notice that it starts to overlap, right? Pi, negative pi over 2, or sorry, negative 2. 7 pi over 6, it's 0. 4 pi over 3, so facing this direction, it's 2. Okay, so it's starting to overlap. Now, this is an example of where, we probably should have put some more points in here. So if I go on either side of, let's say we're going to go either side of this 2. So that'd actually be going from, what's happening at pi over 12 and negative pi over 12. Okay, if you plug pi over 12 in, you are actually, it's similar to the 45-degree angles, because that's 1 pi over 12, 2 pi over 12, 3 pi over 12 is pi over 4. So those pi over 4 spots every 15 degrees are actually pretty important for us. I know the cosine of this spot, if I plug pi over 4 in, cosine of 3 pi over 4 is root 2 over 2. Times 2 is root 2, which is about 1.4. So I'm going to go toward pi over 4. I'm sorry, cosine of 3 pi over 4, that's over here. That's negative root 2 over 2. Times 2 is negative root 2. So negative 1.4. Facing pi over 4, we're going negative 1.4. Takes me to that spot. And if I do that every 15 degrees, I actually am going to get these little spots here. I'm sorry, that's the wrong spot. This is the 15-degree spot, right? Those 15-degree spots are necessary to kind of get the full picture here. That's not the right spot. Okay, so I think I got them all in there. All right, it's tough because it's all pink. I think on your paper it'll be a little nicer because I think yours has every 15 degrees marked. So you have those lines marked for you. All right, so at every 15 degrees, it's going 1.4. So we're actually getting our petals for this rose curve, okay? So you see those 3 petals there? Our first point was 0, 2, and then it's coming toward that point, and then 0, then it goes down here, then it goes up here, then it completes your petal by the time it gets to pi, and then it would repeat. So all the other 3 petals actually overlap. Okay, so that is our polar curve. Now, we can change this, and this is something that you need to be able to do. And we're going to practice this on a really difficult problem tomorrow. But I think that it would be beneficial for you guys to look through in your book. I don't have them done because it's mostly review. But in your book, the first several problems, like 1 through 53, are the review of changing polar to rectangular, vice versa, equations. Pick the odd problems. You can check the answers in the back of the book. And it'd be a good practice to just pick like 1 from each section or 2 from each section for your own benefit, okay? But the other things you should be able to do is to change this to parametric form, okay? So in parametric form, we want x equals and y equals, right? For parametrics. We know that we have a formula for x equals. X equals r cosine theta and y equals r sine theta. Okay? But I can go even further because I know r. So right now there's too many variables in here, right? When we have parametric form, we have x in terms of a single variable, usually t, sometimes theta. It's going to be theta for these. And y equals just one variable. But right now we have 2 variables. So we actually know what we can replace the r with for this problem. So every single time I want to change a polar equation to parametric, I'm starting with x equals r cosine, y equals r sine, and then replacing the r. So I actually get x equals 2 cosine of 3 theta times cosine of theta. Okay? The y value, I get y equals 2 cosine of 3 theta times sine of theta. So now I can find the horizontal location if I know theta, and the vertical location if I know theta. For instance, that first spot, I can get to that spot because I know that's just the x is 2 and the y is 0. So if I plug 0 in to my parametric version, the cosine of 0 times the cosine of 0, 1 times 1 is 1, times 2 is 2, I get x equals 2. If I plug 0 in here, sine of 0 is 0, times all that is 0, I get the point where the y value is 0. I get the point 2, 0. Okay, so this is the parametric version. Tomorrow, in class, I'd like to work on, and I'll zoom you guys in, okay? I'd like to work on how can we change this to the rectangular version. This one's not that difficult, because normally we don't see these things when we have x's and y's in our equation, but we can do it, okay? It involves some properties we got to make use of, but I'm going to let you guys try to do that on your own for a while, and I'll be here to help you with any questions, but then we'll go over it at the very end of class, okay? All right. Oh, I do want one more thing. Graphing calculators. Your graphing calculator will do polar, okay? And it actually will help you maybe speed up making a table. This is because of the BC exam, okay? The AP exam for the BC section. So if I go to mode, I have the functional. This is the 4th tab or 4th row down there. We have the functional notation. We have parametric, which we can use. We have polar, so I'm going to hit polar, and then I can go to my y equals button, and it says r equals. Okay, so I have r equals 2 cosine of 3 theta. I can hit the x button. Okay, it puts thetas in there. I want to make sure that I'm in radians. So in the mode again, make sure you're in radians. Okay, and then I can maybe go to window. Okay. So in the window, it has theta minimum 0, theta maximum put 2 pi, and then it has the decimal version in there, 6.28. Theta steps, I would suggest counting by pi over 12s. Okay, that's every 15 degrees. So for the theta step, put pi divided by 12, at least. Okay. All right, then if you hit graph, you get your problem there. Now, what I want to look at is if I go second table, it actually gives me all of my values for my thetas. I don't know why my thetas are counting like that on my table. Table set. I need to go to table set. Table start should be 0. Delta table, how much to count by, I want pi over 12 in there. Now if I go to table, now it's set up. Okay, so 0, there's my 15 degrees, 30 degrees, 45, what comes after that? 60, 75, 90, and it gives me all those values. So my table I can get, okay? If you want to make your table with your calculator and count by 30s, go to your table set, and in the delta table part, put what you want to count by. And then that's what it'll list in your table. So if you wanted to count by your 30 degrees, put pi divided by 6 in for the delta table. And then when you go to table, it lists 2, 0, negative 2, 0, 2, 0. Exactly what we found. Okay? So if you're allowed to use your calculator, it will help you speed up that process. All right? See you guys tomorrow for a challenging question, and then we'll get to the calculus of polar form. All right? Take care.